another one with you very soon. Kilo 5, Kilo Victor in Texas, from Golf 3 Yankee Papa Zulu, 73. 73, John.
G3YPZ, G3YPZ from Whiskey United 2 Delta. Whiskey United 2 Delta.
From Golf 3 Yankee Papa Zulu, good morning, good afternoon to you, and thank you very much for the call. Name is John, and I'm at Long in Lincolnshire, Long Sutton in Lincolnshire, on the eastern coast of England. Whiskey United 2 Delta from Golf 3 Yankee Papa Zulu.
Okay, John, thank you very much. You're my first contact on this Junkbox rig. This is a radio that I'm just getting on the air. I haven't even got the SWR straightened out yet. Looks like we're about 3 to 1. I need to put the tuner in line. My name is Mike Mexico, India Kilo Echo, and I'm located in the state of New Hampshire, about an hour north of Boston, in Manchester, New Hampshire. Manchester, New Hampshire, a big mill town over here in the 1800s and early 1900s. Running a Junkbox rig. It's a 6146 modulated by a pair of 6L6s. So G3YPZ from Whiskey Uniform 2 Delta.
Whiskey Uniform 2 Delta from Golf 3 Yankee Papa Zulu. Well, that rig's sounding very good. I have a similar one here, an old British KW Vanguard that has that lineup with a 6146 modulated by 2 6L6s, but I'm not using that at the moment. I'm using the Input DX100 with a DBS VFO and running about 70 watts output, receiving on a very old AR88 receiver. And the antenna's a 4-element monoband Yagi. Back she comes, Whiskey Uniform 2 Delta from G3YPZ.
Okay, John, well, thank you so much for being my first QSO on this homebrew rig. This radio, I've been building it over the past month, and I've done a YouTube series on this transmitter, starting out with collecting the Junkbox parts, building the power supply, and then the last video was on the RF chain, and the one that will be coming next week is on the modulator itself, which is a 12AX7 with a 6SN7 long-tail pair of phase into the 6L6s. I'm using military iron. It's a TCS transformer, a TCS modulation transformer from an old Navy low-power transmitter. So it's really nice that this thing's working without paying attention to the antenna SWR. The antenna is a full-wave loop. It's a rectangle. The vertical rectangles are quite popular now. I have nested rectangles for 10, 15, and 20 meters, and they feed a single coax 50 ohm line. So it's a very simple antenna, but it's well up in the air. I think running around 4 to 1 or 3.5 to 1 is probably not the best idea for a brand new radio just on the air for the first time. G3YPZ from WU2D.
Yes, beautiful puppy. No problems at all, Mike, and regardless of your ISWR, it's radiating. And the audio sounds really nice. It's good quality.
Holy cow, it's working. Yeah. Junkbox on the air, that's for sure. And okay, so when you put this much time into a transmitter, over a month, let's say, is that really a junk box at that point? It's a project. Let's call this a project. But it started out as a junk box rig from this old 73 magazine. And it's using parts out of my junk box, so it's got to be a junk box rig, right? You know, as I was searching around in my parts, I found an older radio that I built, I don't know, maybe 15, some sunspot cycle, maybe 2 ago. And I found an older one. Look at this. This is a little one, and it's actually using a pair of 6 V6s and an old SCR 522 modulation transformer, probably good for, I don't know, 7-8 watts. And this thing used a 2E26 in the final. So this is probably about a 7 or a 10 watt output transmitter that I built for 6 meters, 6 meter AM. It's very similar. Of course, it doesn't have onboard power or switching or anything like that. But there's a Junkbox rig from earlier days. 6 V6s. I think the oscillator and driver is a 6AW8, like they used to have in the Heathkit, you know, 2ers and 6ers and 10ers, attempting to drive the 2E26 final. So before I move into the modulator section, a little bit of housekeeping. I wanted to mention a few corrections and improvements on the RF chain. One thing that I failed to take into consideration was the importance of controlling the RF bypassing above the modulation transformer. The modulation was very muddy when first applied, and this was traced to some bypass caps on the screen and plate of the final amplifier. These had been higher values, and I had not changed them out to smaller values for AM modulation. You don't need very much at 10 meters for bypassing. Remember that this had been a linear amplifier before, so the larger caps made sense there. Also, the 12K screen resistor was much too small for modulation, and I came close to burning up the screen grid of the 6146 during the initial connection of the modulator. This screen resistor should be between 27 and 33K at a 1 or 2 watt type value. And I fooled around with various approaches on the input network, always trying to go for more and more grid current. I ended up trying the tuned slug, the cap-tuned toroid with a red-black core, and even a wire-wound, air-type tuned transformer approach. All were virtually identical in performance as far as grid current was concerned. Also, on the medium voltage power distribution off the tap on the high voltage, I went with a star system with each stage having a separate resistor to set voltage, rather than having them all in line with caps in between, as you would have with a hi-fi amp. This improved regulation, transmit to receive. So I do recognize that some of you are not used to electronic drawings or schematic diagrams. I do have a physical movie showing the layout of the modulator. I'll go through the stages in that, but let's look at the schematic first. Now, people get kind of wrapped up with these voltages. I have the voltage points. Everybody's trying to get the exact voltages shown on the chart, but I can tell you, think about it, your microphone audio is at most 100 millivolts. You've got about 1 volt RMS coming out of this first stage. So whether this is 105 volts or it's 205 volts or it's 50 volts, this stage is going to work. As the voltage starts to build up, then it becomes a little more critical that you keep things centered. So by the time you get to your phase splitter, which is driving the grids of the 6L6s, yeah, you do need 20, 30, maybe 40 volts peak to peak of drive to drive the 6L6s. But again, 40 volts peak to peak, when you have a rail of 300 volts, it really doesn't matter what these voltages are. You're going to be okay. These are just target values. We try to bias things in the middle of the load line, but there's a lot of forgiveness with amplifiers, especially amplifiers that are used as modulators, where you're not looking for critical hi-fi distortion. You're just trying to make some power to modulate your single tube Class C RF amplifier. So the microphone comes in between a few millivolts and 100 millivolts. It's got a little ferrite bead and a capacitor that takes care of any RF that might want to come in. Notice it's direct coupled into the first stage, the preamplifier. And the reason we have this 4.7K is, let's say you had a 1K dynamic microphone you hooked up here. Well, if that went straight in, it would short out this 1 meg resistor, which is part of the biasing system of the tube. So we add this 4.7K basically to make sure that no matter what you do out here, you don't disturb the biasing too much. This 470K could be anything between 100K and probably 1 meg, and this thing would still work. Not critical. Then we come out of that microphone preamplifier, which has a lot of gain, probably 40 or 50 dB of gain, and we're up to the 1 volt RMS, probably the few hundred millivolts to 1 volt RMS level, and we have our mic gain control. This second stage here is only necessary because we want to do some feedback and bring some of the output back to the input in a controlled gain stage. So if you didn't want to do that, you could probably leave this out completely and just couple right into this stage. The third stage is a phase splitter. So this is going to go up and this is going to go down. So it drives the 6L6s in a differential manner. This is called a long tail pair, and the way it works is through cathode coupling. The cathode coupling between the stages forces both stages to be at the same gain, and if we actually made R13 into a constant current source, this would almost become a perfectly symmetrical amplifier. But I didn't want to put a constant current source there. I just put a large resistor that is going to put us towards the center of the load line, and as long as this is unbypassed, the two stages will track pretty close, and I didn't see a lot of difference between the two sine waves coming out. They were just 180 degrees out of phase. As a matter of fact, this turned out to be like an 80K resistor, and this guy measured about 85K, and it didn't matter. The two waveforms are virtually identical. So we've got our 40 to 80 volts peak to peak available for the two grids of the modulator stages, the 6L6s. I've set the tubes for 30 milliamps per tube. That's very light into AB. Probably a hi-fi amp would set that a lot higher, possibly 40 or 50 milliamps per tube. We don't need that. And you're going to find the bias is a little bit higher than they set it for hi-fi amps. Finally, I've got a nice snubber network here. This will make sure that at the very, very high frequencies, the ultrasonics in other words, that there is a load represented by this 4.7K resistor. So the high voltage is here, and that goes to the center tap. If you happen to be sharing the high voltage power supply with your final, then this gets connected to this, and they're both approximately the same impedance. It should be a 1-to-1 transformer or something close to 1-to-1. Feedback could be put on the primary side, but normally it's put on the secondary side of the transformer. So everything that's enclosed in this loop will be flattened. The gain will be made up over frequency with the feedback network. So if you want to do some pre-emphasis to get more highs, or you want to get more lows, don't do it in here. Do it over here before you're into the feedback loop, or over here in the RF stage, the screen grid of the tube, the bypassing around the meter. Anything you do in here will be compensated by the feedback network.
So I'm in the middle of wiring the modulator section, and if you place the terminal strips in logical areas, you'd like to minimize the lead length, and you'd like to minimize the number of wires, making the components do the jumping between. Your most sensitive stage, of course, is the input preamplifier. That's where you might have to use some shielded cable and some extra special effort around the connector to make sure you have RF bypassing and grounding done right. But we're at about the 90% level of wiring on the modulator. I just have to run the B+ wires and get the voltages set up on each stage for Class A in the early stages. And I have the potentiometer there, that's the bias, to put the two 6L6s into Class AB. There's nothing special about this long tail pair phase splitter. This phase splitter is not using a constant current source. It's just using a tail resistor of 47K, and a pair of plate resistors, 82K, and then it's got a 1.6K resistor that's setting the bias for the load line for the 6SN7. And when we look at the output, you can see it's well matched. No trouble with this phase splitter. I'm not going to go any further because this is a modulator, not a hi-fi. And we're showing 100 volts peak to peak of drive available for the 6L6 grid, so that's way more than is necessary. So I'm not going to go any further with the long tail pair phase splitter. Let's take a little tour around the bottom of the transmitter. I think we've covered the power supply pretty well. I didn't mention that I am using a TR relay here, and all this does is this applies B+ to both the oscillator and the driver. The final amplifier is biased class C, so it doesn't really draw any current when you're not in transmit, so that just sits there waiting for a signal to come out of the driver. So I have the modulator section built in, and it's tested and working. The microphone input here, it goes into the first section of a 12AX7, and then into a potentiometer, which is the mic gain control. After the potentiometer, it goes into the second stage of the 12AX7. So this is your speech amplifier right here. Pretty good size signal to go into your phase splitter, and the phase inverter or phase splitter is a 6SN7 differential amplifier called a long tail pair, and this produces the anti-phase and in-phase signals that are sent to the two 6L6s. This allows you to get away from having to use an interstage transformer, a push-pull interstage transformer to drive the 6L6s. Instead, we're doing it with the phase splitter. The 6L6s themselves are running in class AB, fairly light, about 30 milliamps per tube resting current. Now, if you're a hi-fi enthusiast, you'd probably say that's a little bit light. You should run a little more current. But for the modulator, I wanted to be easy on the tubes, and I kept it at 30 milliamps per tube. Now that's set with this potentiometer here, which is the bias adjust control. As a luxury, to even out the modulation transformer, which is military iron out of the old TCS transmitter, I did do some negative feedback. And the negative feedback comes off the secondary of the transformer through this high voltage 0.25 microfarad capacitor. And that is fed all the way back to the second stage of the 12AX7, which has a degenerative cathode with a split resistor setup, and that's where I inject the negative feedback. And this, of course, lowers the gain in accordance with how you set this particular pod here. So this is the feedback pod working in conjunction with this capacitor. I've got about 6 dB of feedback in line right now. So that's the entire modulator section. Pretty straightforward. Plenty of gain off a dynamic microphone.
So we are getting close. This is the place where you're getting excited that the project is coming together and you rush to see if you're going to actually get modulation. But this is also the time that mistakes can happen, and severe electrical shocks are most likely. So be careful. The RF section will remain unkeyed during this modulator section only testing. The RF amplifier B+ is disconnected completely. Yes, we can think of the modulator as nothing more than a public address amplifier at this point, keeping in mind that the output impedance is not 4 or 8 ohms, but several thousand ohms. Roughly 450 volts divided by our 80 or 90 milliamps, so that comes out to 4,500 to 5,000 ohms. And we need to be able to measure 20 to 30 watts of output power. Obviously, you need power resistors as your load. So that comes out to an RMS voltage of between 300 and 350 volts if you want 20 watts of power. Your RMS voltmeter and certainly your scope may not be happy with that kind of voltage. So I formed a 10 to 1 voltage divider with the load. In this basic test, the B+ is cut from the load side and we simply connect and measure, similar to a hi-fi approach to amplifier testing. But remember that unlike your citation amplifier, the transformer secondary also has DC current running through it. This could well saturate the core and cause distortion or undermodulation or transformer heating, even breakdown. So running it with high voltage running through or high voltage attached required that I added an isolation capacitor between the transformer and the scope. I actually did make sure that I saw 20 watts of clean power at 700 or 1000 hertz, but I did all subsequent testing, including frequency response testing, at about 5 watts output.
As you can see, the modulator is now completed. Over here we have the 12AX7 tube, which is the mic preamplifier. 2 stages. The first stage is out of the feedback loop, basically just brings the microphone up to a fairly high level. That stage has high gain and goes into the mic potentiometer, sets your input from your mic. The second stage is basically where the feedback is introduced, so it's a gain controlled stage, lower gain. Then I'm going into a dual triode. It's a 6SN7 medium mu triode that I'm using as a phase splitter. This gives me the positive going and negative going waveform to drive the 6L6s. And that's known as a long tail pair, a very common way of driving a pair of pentodes. And we have finally the 6L6s are producing the 20 or so watts that we need to modulate the radio. Now I did threaten to use a different tube, the old 6DQ6, and I think I'm going to go as far as to substitute this in, and we can try the 6DQ6s. These are very low cost television tubes from the late 50s. Still available at low cost, both new, old stock, and used. So that's the rundown on the modulator as far as how it looks.
So what I like to do when I'm sweeping an amplifier is set it up to put out about 4 or 5 watts, and then 700 hertz. I set the 0 point, and then I just look at how the thing acts as I go from 700, and then you check the low end, 600, 500, 400, 300, 200, 100. Okay, it's got a great low end. This amplifier is fantastic on the bottom end. So then we go up to 1,000, peaking up just a little bit, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. Okay, this is exactly what you expect, 10,000. This is what you'd expect with an amplifier with no feedback, with a piece of military modulation iron. You know, it's going to be down as you get above 5 kilohertz. You know, you're down 3 dB at 5 kilohertz. It's actually not bad. It's not a bad amplifier. So let's hook up some feedback now. Let me go back to the 700. That's where we set our 0, remember? Now I'm going to hook up the feedback, and we'll try this again. Okay, with my feedback in, I'm 6 dB down. Let's start there. Let's bring our output back up to 0. Okay, we're back at 0 at 700. So let's go back down. 500, 400, 300, 200, 100. Beautiful. Flat as a board. Okay, and then let's go to 1,000. 1,000, it's up just a touch. 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. Okay, with that much feedback, remember at 5 we were down 3 dB. Now we're down only 1 dB with the feedback at 5,000. We're down 1 dB. So the feedback did help. So if we add a little more feedback, okay, we'll go back to 700. It's coming in awful fast, but okay, I added some feedback.
Okay, now let's bring our gain back up again. Repeat our process. 600, 500, 400, 300, 200, 1. Back to 1,000. Okay, that's 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000. It's flat as a board all the way up. For the next scale, you'll see this better. No matter where I go, I'm at 10,000, 9, 8, 7, 6, 5, 4, 3. That's what happens when you have excess feedback. So of course it took away almost 12 dB of gain. So we probably don't need that much feedback. But you see how feedback can flatten out even a piece of military iron. So another test we can do while we're here is basically the frequency response of the modulated signal. Put this back in. So let's change the frequency. Let's go down first. Okay, I've gone down to 100 hertz. Wow, this thing has really good low response. That's from the feedback. Believe me, the military iron probably is not very happy with 100 hertz signal. That's 300. Just hanging in there nice. 700. 900. 1 kilohertz. 2 kilohertz. Little bit of triangle distortion at 3 kilohertz. 4 kilohertz. 5 kilohertz. Now, the receiver's set up for a 6 kilohertz bandwidth, so it's starting to cut in, and you're not hearing as much. But you can see the modulation's still pretty good. 6 kilohertz, 7, 8. Down a little bit. Not bad, though. 10 kilohertz. And again, hanging steady at 20 watts output. So I'm now into a dummy load, and it's pretty apparent that I do have some distortion, especially over that 30% level where we were testing. If we were to do a trapezoid pattern, I think you'd see some kinks in it. And I think I could use a little bit more high end. But this is fairly normal for modulating tetrodes with a very simple system, like using just a resistor and everything above the modulation transformer. So this is going to be the end of this video series, but I will do one bonus video where I try to improve the modulation by using some better techniques, and we try to clean up the audio a little bit. I hope you've enjoyed this series on building a Junkbox transmitter and the fun of going through all of the different parts of the project.